All right, today we're going to talk about something you probably never think about, but they are absolutely everywhere. Control valves. These are the powerful, totally unseen gatekeepers that manage the flow of, well, pretty much everything in our modern world.
I mean, just think about it for a second. The water that comes out of your tap, the gas for your stove, the steam that generates power in a plant, all of these are fluids, right? And they all need to be managed super precisely. That fundamental challenge, controlling flow, that's where our story really begins.
So, what exactly is the hero of this story? Well, at its most basic, a control valve is, you guessed it, a valve that controls things. It's a device that sits inside a pipe and basically acts like a gate, regulating exactly how much fluid can get through. It's a simple concept, sure, but it's incredibly complex in practice.
Okay, so to really get this, we've got to pop the hood and see what's going on inside. Let's take a look at the anatomy of one of these gatekeepers.
Here we have a cutaway of a really common type of valve. It's called a globe valve. So let's break this thing down. First up, you've got the body. That's this tough outer shell right here. Its whole job is just to contain all that pressure and protect all the important bits and pieces inside. Now, inside, this is where the magic really happens. You've got two key parts. The plug, that's the bit that moves up and down, and the seat, which is stationary. When that plug pushes down into the seat, bam, you get a perfect seal, and the flow stops.
So, what's making all this move? That's where the stem and the actuator come in. See, the stem is just a rod that connects that internal plug to the external actuator. In this case, it's that hand wheel up top. The actuator is what provides all the force to control the flow with incredible precision.
But of course, you can't just have one type of valve for every single job. That would be way too easy, right? Different problems need different designs, and they generally fall into two main categories based on how they move.
So the first big way we can split these up is by their motion. You've got your linear motion valves. Think of the plug moving straight up and down, kind of like a gate. And then you have rotary motion valves, where the part that blocks the flow just rotates, usually only a quarter turn, to open or close.
And this slide just shows that difference perfectly. I mean, look at this. On the left, you've got that linear globe valve again. The plug moves up and down, and it forces the fluid through this kind of complicated S-shaped path. But on the right, that's a rotary butterfly valve, way simpler. It's just a disc that turns 90 degrees to let the fluid shoot straight through.
So why does this matter? Well, these different designs mean they're used for completely different things. You can see it right here in this table. The globe valve, with its tricky path, is amazing for throttling, which is just a fancy way of saying you can precisely control how much flow gets through. The butterfly valve, on the other hand, is more of a simple on-off switch. It's fast, it's lightweight. But here's the trade-off. That complex path in the globe valve creates a high pressure drop. Meanwhile, the super simple butterfly valve, barely any pressure drop at all.
And this whole idea of pressure brings us to a huge challenge in valve engineering, because managing all that force can create this, well, this hidden enemy, a destructive force that can literally rip a valve apart from the inside out.
Now, this might sound a little weird. You'd think the problem would be high pressure, right? Too much force. But what happens when the pressure inside a valve gets dangerously low? Okay, let's just follow the physics here for a second. As the fluid gets squeezed through that really narrow opening between the plug and the seat, its speed goes way, way up. And just like on the top of an airplane wing, when velocity increases, pressure drops sharply. Now, if that pressure drops below the fluid's vapor pressure, it literally starts to boil. It forms these tiny little vapor bubbles right there inside the valve.
Okay, so now you've got these bubbles. Two things can happen. If the pressure on the other side of the valve stays low, the bubbles are fine. They just stay as bubbles. We call that flashing. But, and this is the big one, if the pressure recovers as the pipe widens again, those bubbles violently collapse back into liquid. And that, my friends, is called cavitation.
And let me tell you, cavitation is the real villain of this story. Each one of those bubble collapses is like a tiny microscopic explosion. It creates these little microjets of fluid that just slam into the valve's internal parts at incredible speeds. The result? You get physical damage, just chewed up metal. You get unacceptable noise, terrible vibrations. It just destroys the valve's efficiency and its lifespan.
So, how in the world do you fight an enemy that's made of collapsing bubbles? Well, it all comes down to smart engineering. It's about making the right choices long before that valve ever gets put into a pipeline.
Engineers actually have a whole playbook for this. For starters, they can pick valves that are specifically designed to minimize those big pressure drops.
They can also use incredibly hard materials like this alloy called stellite on the plug and the seat to resist all that damage. They also know that certain designs, like those ball and butterfly valves, are just more likely to have cavitation, so you have to be really careful about where you use them.
So the next time you turn on a faucet or you see a massive pipeline, just remember those gatekeepers working away inside. These control valves aren't just simple chunks of metal. Nope, they're the result of really critical engineering choices, constantly balancing pressure and flow and fighting this invisible battle against self-destruction, all just to keep our world running smoothly and safely. Makes you wonder, what other unseen engineering are you relying on every single day?